Hello guys, a very good evening to all of you. Today in this video we are going to discuss a very important topic, that is ortho effects in organic chemistry, right? So there are basically three ortho effects in organic chemistry. First one is in the acidity, second one is in the basicity, and the third one is in the aromatic electrophilic substitution of the benzene ring. Okay, so the third one, that is in the electrophilic substitution, that is very straightforward. Okay, that will take maximum of 1 to 2 minutes. So we are going to discuss at the end of the video. So first we are going to discuss the first two, that is in the acidity and the basicity, that ortho effect in the acidity and the basicity, right? So let us start our discussion with the acidity, that is ortho effects in the acidity. So from the very beginning, you just remember that acidity, the ortho effects in acidity is specifically to the benzoic acid. Okay, so only one acid that we are going to apply the ortho effect, that is benzoic acid. No other acid than benzoic acid, right? So only benzoic acid, so your ortho effects. That means the ortho effect is only applicable to the benzoic acid, and the basicity, only aniline is the only base in which we are going to apply our ortho effects. Okay, just remember two things. First one, from the very beginning, from acidity is only benzoic acid, so ortho effects, in the basicity only aniline, so ortho effects, right? So let's start our discussion with the acidity. So we know the acid, right? So any acid, so any substance is acid if it is going to give a H plus, right? I am talking about the organic acid basically. So if I have this benzoic acid, so say for example this is a benzoic acid. Okay, so obviously it will give H plus along with a conjugate base. This is a conjugate base, this is a benzoate ion. Okay, so the acidity of that substance depends on what? Depends on the stability of the conjugate base. So if it is an acid, this is our conjugate base, right? For any acid having H plus, that means if after the donation of the H plus, they will give a conjugate base. Okay, from the Bronsted and Lowry acid base concept, the conjugate acid base pair theory, we know that any acid after donation of H plus, whatever we remain, okay, we have remained, that is our conjugate base. So the acidity, the property of the acid, that means how stronger acid will be, that depends on the stability of the conjugate base. If the conjugate base is more stable, the given substance is more acidic. If it is less stable, it is going to be less acidic. Like how? Where? Because if the stability of the conjugate base is more, then the acid will try to give H plus and form conjugate base, right? So that's why if the stability of the conjugate base is high, your acidity of that acid will be high. Okay, now question is, how can you stabilize this conjugate base? This is the question. How can you stabilize this conjugate base? Now as you can see, there is a negative charge on the oxygen atom, okay, on the conjugate base. So in any means, if you are going to withdraw that negative charge, that means the conjugate base will be stabilized. So how can we do that? By attaching the electron withdrawing group. So if an acid, okay, this is your benzoic acid, and if we are going to attach the electron withdrawing group, that means this will withdraw the negative charge on the conjugate base after donation of the H plus. This electron withdrawing group stabilize the conjugate base, so that means your native acid will be more acidic. Okay, if we attach the electron withdrawing group, what is electron donating group, what happened? It will provide the electron more, and the electron density on the oxygen will be pronounced. So in that case, your stability of the base will be less, and the acidity of that acid will be less. So what we learned is, or what we discuss is basically very straightforward in one sentence, that is electron withdrawing group decreases the acidity, electron withdrawing group enhance the acidity, and electron donating group attached in its acid that will decrease the acidity. Electron withdrawing group increases or enhance the acidity, and electron donating group decreases the acidity, right? That means if I have this benzoic acid and I attached electron withdrawing group, that will be more acidic than normal benzoic acid, and this will be more acidic when we are going to attach a electron donating group, right? So this is the scenario of the acidity. Okay, we know it already. We know from earlier classes, we know this concept we already know from acid concept theory, right? So electron withdrawing group enhance the acidity of this group, that acid, and electron donating group reduces or decreases the acidity. Okay, but what is the ortho effects? Okay, we know. So if you have a doubt of this representation, so this way of representation represents the attached of the electron withdrawing group at any one of the position of that ortho para, whatever the position will be. So this can be represented like this. Okay, that means the electron withdrawing group is attached somewhere over here, right? So if the electron withdrawing group is attached in an acid, that will enhance the acidity of that acid, and if the electron donating group is attached to that acid, that is decreases the acidity. Okay, so now what is ortho effects? So ortho effects say that, or the states that, the ortho effects states that any acid in which there is a ortho substituted things, right? Any ortho substituted benzoic acid, that means it's very acidic. Okay, I said earlier that ortho effects only applicable to benzoic acid, right? So if you have any benzoic acid in which there is a ortho substituted group, that group, irrespective of the nature of that group, either it will be electron donating, either it will be electron withdrawing, doesn't matter. So any group attached at the ortho position of that benzoic acid, that will, the acidity of that group, that acid will be more. That what I mean is, suppose this is my benzoic acid, and at the ortho, this is ortho, this is meta, and this is para. So at the ortho position, what I am going to do is, I put a group like G. So G is any group, and this nature of the group is irrespective. It doesn't depend on what is the nature of the group G. It may be a electron donating group, or it may be electron withdrawing group. So this acid, the acidity of this group, this acid will be more as compared to the normal benzoic acid. So this is the ortho effect. So ortho effect states that your ortho substituted benzoic acid is more acidic than normal benzoic acid. So this is ortho effect. Okay, so you put a electron donating group, doesn't matter. You put a electron withdrawing group, doesn't matter. Any group that will present at the ortho position, okay, that benzoic acid will be more acidic. So this is what the ortho effect is in the acidity of the benzoic acid. Okay, now let us find out the reason why it is so. Okay, we will discuss in details the reason. So what is the reason? So reason is, there is a concept called steric inhibition of resonance. There is a concept called steric inhibition of resonance. Is short form, it is called SIR, SIR, steric inhibition of resonance. So reason is steric inhibition of resonance. Okay, whether it is a concept. Okay, there are many applications, there are many effects of this steric inhibition of resonance. So one of the effect is the ortho effect, right? So this is the reason, the steric inhibition of resonance is the reason of your ortho effect of the benzoic acid. Okay, so if anyone going to ask you, you must say, if anyone is going to ask you the reason of the acidity, that the ortho effect of in the benzoic acid, that you must say the reason is steric inhibition of resonance. So now we are going to discuss that what is SIR each, that is what is SIR each. Okay, so the steric inhibition of resonance is basically, suppose I have a benzene ring like this. I have a group A and I have a group B. Okay, suppose I have a group A and at the same time at ortho position I have a group B. Okay, so let's assume that this A is not in conjugation. That means this is not going to take part in conjugation with the benzene ring, where the B is conjugating. So B is in the conjugation, this is not in conjugation. And suppose say and B is bulky. Bulky means it is a bigger molecule, right? So this B is a bulky molecule and is in conjugation with this benzene ring, and A is a normal group, any group that present ortho to the bulky group. Okay, so what we know, that we know from the resonance. So there are basically two most and prime criteria of a molecule to show resonance. What are they? First one, there must be conjugation. There are two prime criteria for resonance. What are they? First one is there must be conjugation. If there is no conjugation, there is no resonance. So there must be conjugation, and any group that participate in the conjugation must be remain at the same plane. Okay, so there are two prime criteria for a molecule to show resonance. One is there must be conjugation, and whatever the molecule, how many number of molecule getting participate in that resonance, that must be present at the one plane, that means the same plane. Okay, this is the these are the two most important criteria of a molecule to show resonance. If any one of the criteria is not occurring in a molecule, that is, there is no going to resonance going to take part, right? So that means now what is most important? The plane. The molecule must remain in the one plane. That means the molecule should be planar, right? That means the molecule should be planar. Okay, suppose you are going to move through a vehicle, right? You are going to drive a vehicle. So now your car or bike, you can turn any direction. You can go to the left, you can go to the right, anywhere. But suppose assume you are in a vehicle called resonance. Okay, resonance. Suppose you call name your car or name your bike is resonance. You are traveling through your by your resonance car, that the condition is you cannot go left, you cannot go right, you only can go straight. That means the resonance, that means the molecule should be in one plane. The out of plane, if there is a condition of the outer plane, that the electron is not going to like this, not going to flow like this. The electron only flow from straight line in a one plane. Okay, this is the criteria of resonance. Okay, so the B was initially in the conjugation, it is bulky group, and there is another group at the ortho position. Okay, so what happened? Now as it is bulky and there is another group at the ortho position, now here the van der Waals radius of that B will be in repulsion with the van der Waals radius of A, because this is bulky. Okay, now there must be a repulsion again. Now there must be a repulsion between the van der Waals radius of B and the van der Waals radius of A. That means now these two group now is in repulsion. So what is the result, or what is the consequences of this repulsion? Okay, so suppose, say for example, suppose this is my benzene ring. Suppose this is my benzene. This is in one plane, and suppose this is my A. Okay, this is my A. This is A, whatever the group is, and this one is my COOH group. So my bulky group. So for example, this is a bulky group. It is in conjugation, right? So all are in one plane. If you see, all are in one plane, right? So as this repulsion takes place between these two molecules, so what is the consequences? Now this group will push this particular group out of the plane. Okay, so what is happening? This group will push this group, any group that is present at the ortho will push the conjugating group out of the plane. Now initially this group is in conjugation of the benzene. Now this group is above the plane or below the plane. So in either direction it is going to be divert. So now this group is not going to be take part in the resonance, that is inhibit. Okay, this group will inhibit the process of resonance. That is why it is called steric. Steric means the bulkiness. This is a steric repulsion. Okay, now this is called a steric inhibition of resonance. That means this group will now inhibit this molecule to out of resonance. That means this B is not going to take part in the resonance. That is why it is called steric inhibition of resonance. I think the concept is clear. Now we are going to apply this steric inhibition of resonance in our benzoic acid, ortho substituted benzoic acid, so that we can understand our ortho effect in benzoic acid, right? So this is my benzoic acid. This is my benzoic acid, right? So after donation of the H plus, we have the benzoate ion like this. Okay, now tell me, this group is an electron donating or electron withdrawing group to this benzene. So this is a electron withdrawing group and this is a electron donating group over here. So if you are confused with the electron donating, electron withdrawing group, how do you recognize the electron donating, electron withdrawing group? So suppose you have a benzene ring. Okay, in the benzene ring, suppose you have a group A and this group have negative charge or lone pair of electron. That means this will donate the electron. So this A is said to be electron donating group. Now if the A is going to donate the electron, now this benzene ring is going to withdraw the electron. अगर एक देने वाला है तो एक लेने वाली तो होना चाहिए ना, लेकिन एक लेने वाला ही नहीं तो देके क्या फायदा. तो so this A will donate the electron, so this benzene ring will withdraw the electron. So for this one, this benzene is minus M group and this is plus M group. But you have a electron withdrawing group. So how can you recognize electron withdrawing group? Suppose there is a benzene ring, suppose A double bond this is a general scenario. Okay, so if you have found this particular moiety, that you can decide this group is electron withdrawing. And the most important criteria is the B is electronegative group. The B is must be electronegative group. Okay, say for example C triple bond N. Okay, double bond or triple bond might be there. Okay, so the N is more electronegative. So in that case also, this is A double bond B, where oxygen is electronegative, we know. So that we can decide, so that we know this group is electron withdrawing group. So if it is a electron withdrawing group, so what is the plus M or minus M will be your benzene? This will be plus M. Okay, so the benzene can be plus M, so plus M property, or can be withdraw as the minus M also. Okay, that depends on the what type of substituent you have attached to that benzene, right? So we have this benzoate ion. Okay, now this is electron withdrawing group. Okay, so this negative charge, so this pi electron can be donate like this, and the conjugation takes place the benzoate ion like this. Okay, so this is the way the conjugation takes place in the benzene ring. Now as you can see, the benzene is donating the electron through plus M. That means your negative charge over here will be increased, because this group is in conjugation with this. So this negative charge will now be increased. Okay, but this is to be, if you are going to stabilize this negative charge should be reduced. Okay, but this benzene ring is going to donate the electron. So how can you say that this benzoate ion is stable? Right. So what we are going to do is, if anyhow this group, you will make this group out of the plane of this group, this benzene ring. Suppose initially this is your COO minus group and your benzene ring. So if anyhow you can do this one. Okay, so now there is no conjugation. So if there is no conjugation, so there is no plus M of benzene. So if there is no plus M of benzene, so your negative charge will be now not going to be increased. So as compared to this one, if you put a ortho substituted group, ortho group, that will cause the steric inhibition of resonance that we discussed earlier, that will cause this group to go out of plane. So if it is going out of plane, that means it is not going to take part in conjugation. That means that plus M benzene it doesn't work. It is not going to take part of plus M. So the negative charge of oxygen is not going to be destabilized. Okay, so that is why if you put any group at the ortho position, now this is now out of plane. So this plus M not occurs. So if the plus M not occurs, then the increase of electron density of oxygen is not occur. Is not going to be happen. So you can somewhat stabilize the benzoate ion as compared to the native benzoate ion. Right, so that we can say that ortho substituted benzoic acid is more acidic than the normal benzoic acid. Right, so this is what the ortho effects in benzoic acid. So let us take an example. So let us take examples, like suppose we have benzoic acid. Okay, I have NO2 at the ortho, COH, NO2 at the meta, COH and the NO2 at the para position. Okay. Now tell me what is the order of the acidity. Now tell me the order of the acidity. So without any doubt, without any, you do not have to look at the molecule. Okay, the NO2 is in ortho, so it will be more acidic, because due to the, we said that any group or at the ortho position of the benzoic acid, that will be more acidic. So now you have to decide between second and third. Okay, so one is the meta product and the para. So what you have to do is, now you have to find out by the general method. Okay, now NO2, we know the electron withdrawing group. Now I just said earlier, why NO2 is a electron withdrawing group? Because the N double bond O and O minus A, I just written what? A double bond B, where B is more electronegative. Just look at this N is A, is oxygen is B, where oxygen is more electronegative nitrogen. So that's why your NO2 also a electron withdrawing group. So both NO2 is a electron withdrawing in both the case. So we do not have to bother about the group. We have to, the problem is the position. So it is a meta position and it is a para position. So one thing you know from the resonance, so there is no resonance at the meta position. So resonance occurs only at the ortho and para position. Okay. So the NO2 here only minus, observe only minus I. This there is only minus I effect of NO2, because due to the electronegativity of nitrogen and the carbon difference, the electronegative difference of nitrogen and carbon, so that will push the that will withdraw electron through sigma bond through our inductive effect, only minus I. Minus M is not going to be it is not going to be here. Okay, because there is no resonance at the meta position. But here there is minus M and there is also minus I. So this will withdraw more electron. So the acidity of that one will be more as compared to at the meta position. So what is the order? I, then second, then third, then II. So this is the order. Then this is how we are going to deal with the acidity in case of benzoic acid. Okay. So what is the exception? Only one exception is there. What is the exception? Suppose if I am going to say this is your COH group and at ortho you have a hydroxyl group OH, and like this. Now this is more bulkier than OH, so you think, so this cause more steric inhibition resonance, so this will be more acidic than this, but it is not so. The ortho hydroxy derivative will be more acidic. Why? Because in this case the intermediate, that is our conjugate base, the conjugate base is stabilized by the hydrogen bonding. How? This is our benzoate ion and you have like this. Now there is a hydrogen bonding like this. Okay, so you have 1 2 3 4 5 6, your 6 membered transition state intermediate by hydrogen bonding. So that's why due to this hydrogen bonding stabilize the conjugate. Now if there is hydrogen bonding, now this negative charge, you take part in the hydrogen bonding, so there is no further negative charge, so it will stabilize. So due to the hydrogen bonding it will stabilize. So that is why if there is a OH group at the ortho, so that will be more stable as compared to this one, even though this is a more bulkier than OH group. Right, so this was an exception, and except this one, you have any group at the ortho position, that benzoic acid will be more acidic. This is for sure, right? So this was the ortho effect in the benzoic acid. So let's discuss our second ortho effect in the basicity of aniline. Okay, so we know aniline is this. Okay, now we know aniline is a base. Why it is a base? Because of the lone pair of electron on the nitrogen atom, it can accept proton. So any substance then can accept a proton, that is a base. Okay, so after accepting H plus, what you get? We get NH3. This is a anilinium ion. So if it's a base, this is called a conjugate acid. So if it is base and is a base, so it is called conjugate acid. Like in the same way, if the stability of the conjugate acid is more, your basicity of the aniline will be more. Okay, as you can, so you can see over here there is a lone pair of electron on nitrogen. Okay, so there is only hydrogen on all the position. So if I substitute a electron donating group to this benzene ring, what will happen? That will increase the electron density over the nitrogen. So the tendency to attack this H plus now increase, right? So if I attach the electron withdrawing group, what will happen? That will withdraw the negative charge, that will reduce the negative, the lone pair of the negative, the electron density on the nitrogen atom. So to attack H plus, it will be very difficult. So that for any base, okay, if you have a electron withdrawing substituent attached to that base, that will be less basic, and if you have electron donating group that to that base, that will be more acidic. So that is what opposite to the acid. So if you have a acid, if you put electron withdrawing group, that will be more acidic. If you put electron donating group, that will be less acidic. But in case of base, if you are going to put electron donating group, that will be more basic, and if you put a electron withdrawing group, that will be less basic. Okay, so this is what the acid pair, the acid base concept is, right? So I can write aniline. So this is aniline. So if it is attached by electron donating group, so in any position there is an electron donating group attached, so that will be more basic as compared to the normal aniline, and that will be again more basic than if it is attached to electron withdrawing group, right? So this is general scenario, but at the ortho position this is very special. Okay, so the ortho position there is a very special concept that is called your ortho effect in the ortho effects in the aniline. Okay, so what we discussed in the acid ortho effect, so any group attached at the ortho in the benzoic acid, that benzoic acid will be more acidic. So that ortho effect is opposite to that one, this one. So in case of aniline, if you put any group at the ortho, then the aniline will be less basic. That will be less basic. Okay. How we are going to discuss? See, I have a aniline. If I put a CH3 group and I have normal aniline. Okay. Now we know the CH3 moiety is a electron donating group through hyperconjugation as well the inductive effect. This is this CH3 group, so plus I effect as well as plus H effect, right? So this is electron donating group. Now if it donate the electron to the system, now the electron density on the nitrogen will increase. So the tendency of the A's to attack the H plus will be more. So this should be more basic than this. So this should be more basic, but this is not so. So that is what I said is the ortho effect of aniline. So any group you put at the ortho of the aniline, that will be less basic. And the reason is, what is the reason? Reason is steric inhibition of protonation, not the steric inhibition of resonance. So in the case of benzoic acid, that what we discussed ortho effect in benzoic acid, what was the reason? The reason was the steric inhibition of the resonance. Steric inhibition of resonance, that is SIR. But in case of the ortho effect of aniline, the reason is steric inhibition of protonation, and this is in short it called SIP, steric inhibition of protonation. So now we are going to see that what is steric inhibition of protonation. Okay, so you have aniline, it will, suppose you have ortho substituted CH3, ortho substituted aniline, and you have the H plus. So this will attack H plus as it is a base, so it has a tendency to accept proton. So initially you have NH2, now it HH, so the lone pair is now participating in the bonding with the H plus, so there is a positive charge on the nitrogen, and you have the CH3. Okay, so if I write like this nitrogen, this is a H, this is a H, and this is a H, and this is positive. Okay, now the NH2, this NH2 was initially small. After attached to another H, now this is somewhat bulky, H compared to normal NH2. Now there could be possibility of the repulsion between these two. There is steric hindrance between this CH3 group and your anilinium ion. So this is called what? Anilinium ion, orthosubstrate anilinium ion. So this NH3 moiety and your CH3 moiety, there must be a repulsion, because it after attached to a H plus, now it is going to have a bigger size, right? So that it has a repulsive force between this NH3 plus and this CH3 moiety. So this conjugate acid is now stable or unstable due to the repulsion. This will be unstable because of the repulsion. So the aniline is not trying to get the H plus to have this one, because after attaching the H plus, it is not going to be stable. As I said earlier, if the conjugate acid is stable, then only your base is a base, is a good base. If it is not going to stabilize, it is not going to attack the H plus. That means it is not going to be a base. What is the property of base? The base is going to accept a proton. If it is not going, after accepting the H plus, it is not going to be stable, then why it is going to attach the H plus and become the unstable anilinium ion? It is not going to execute like this, right? So due to this repulsion, this protonation is not. What is the protonation? Protonation basically the acceptance of the proton. That is a protonation. Now due to the steric repulsion, this protonation is not occurs, and that is why it is called steric inhibition of protonation, or steric inhibition in protonation, SIP. Okay, so that is why any group at the ortho position, okay, in the aniline is going to be less basic as compared to the normal aniline. Okay, so if I give an example, suppose there is a CH3, there is two ortho position, and in the both ortho position we have two CH3 group. In another case, you have one CH3 group at the ortho, and you have normal aniline. So what is the order of basicity? So if you are not aware of this steric inhibition of protonation, what could be your answer? Because this CH3 group donates the electron, because it is a plus I and plus H effect, this so plus H and plus I effect, so it will donate the electron. If it is going to donate the electron density on the nitrogen will increase, so that it will be more basic. So you could mark like this. But now we knew that there is a concept called ortho effect in alanine, because once there is substitution of ortho, so after accepting the H plus, there is a bulky, there is a steric hindrance created between these two moieties, so this is not going to be accept the H plus. Okay, so this is where this is your order. So if the moment you put any group at the ortho to the aniline, that will be less basic, and this is what it is, your steric inhibition of protonation, and that cause the aniline less basic. Okay, so this is our discussion about the ortho effects on the acidity and the basicity. Okay, now let us discuss the ortho effects in the electrophilic substitution reaction. Okay, so this is very straightforward. There is no such explanation on the third ortho effect. So generally it is a statement. Okay, suppose you have chlorine like this. Okay, and at the meta position you have a electron withdrawing group. Okay, this is a benzene ring. In one position we have the chlorine, and chlorine we know is the ortho and para directing. This is electron donating group, plus it is so plus same effect. And the NO2 at the meta to this ortho para directing group. That means the electron withdrawing group is meta to the electron donating group. You have benzene. In one position you have electron donating, and in one position we have electron withdrawing. And what is the relation? The relation is ortho meta. Okay. Now if you have this system and you are going to carry out a reaction of electrophilic substitution. Suppose I take concentrated HNO3 and concentrated H2SO4. This is a reagent for titration. So what does it will form the nitration product. So what's the possibility? This is Cl initially this. Now the extra NO2 can be possibly attack this one, or can be possibly NO2 at ortho. So what should be the major product and what should be the minor? So this is your major product and this is your minor product, and this is what the ortho effect in the electrophilic substitution reaction. What is the ortho effect? Ortho effect said that in the electrophilic substitution reaction, if you have a system like this, in one position you have a electron donating group and in one position electron withdrawing group, and we know that electron withdrawing group are generally meta directing and electron donating groups are generally ortho and para directing, right? So the external, if you have a dye substituted benzene like this and you are going to carry out another electrophilic substitution reaction, so in that case the another electrophile will attack at the ortho to the meta directing group. What I said? Ortho to the meta directing. Meta directing means electron withdrawing group, meta directing group. The third electrophile will attack at the ortho to the meta directing group. This is not going to ortho to the ortho and para electron donating group. So this extra electrophile will now be take the position of ortho to the electron withdrawing group, and there is no such explanation that why it is happening in the literature. Okay, there is no satisfactory explanation to this one. Okay, so this is the concept, this is the only statement that if you have a dye substituted benzene, one is electron donating, one is electron withdrawing. If you carried out another electrophilic substitution reaction, then another electrophile will attack or take the position ortho to the electron withdrawing group. That means the meta directing group. Okay, if I take another example, say for example, I have benzene, you have CS3 and this is COOH. This is your system, and you are going to carry out chlorination. Okay, you are going to give the chlorination product. Okay, so this is electron withdrawing group. I said many times in this video, that is if you have a system like this, A double bond B, here also C double bond O minus or OH. So A double bond B, where B is more electronegative, so COOH is a electron withdrawing group, and this CS3, I said that this CS3 is a electron donating group through hyperconjugation and the inductive effect. So this is a electron donating group, this is a electron withdrawing group. We have the system like this, that means dye substituted benzene, and we are going to carry out another electrophilic substitution reaction, that is chlorination. So in that case what happened? So I said that what is the ortho effect? The chlorination occurs at the ortho to the electron withdrawing group. So this product is not going to be formed. If it is formed, this is a minor product and this is your major product. This is the ortho effect in the what? In the electrophilic substitution reaction. Okay, so let me give you a question. You answer me in the comment section if you can. Okay, I am not going to discuss the answer. If I have benzoic acid and I have CS3 in the ortho, and another case NO2 at the para, and chlorine at the meta. So you have 3 molecule and you have to decide which is more acidic and which is less acidic, and what is the order of the acidity above the two among the 3 species. Okay, just think and give it in the comment section. So guys, this was the very details video on the ortho effects. So you cannot find another ortho effects on the organic chemistry. Okay, so there was only 3 ortho effects. I discussed very thoroughly all the one by one. Okay, so hope you like it. If you like it, then please give it a thumbs up and please subscribe to the channel. If you subscribe, it will motivate me to make such more interesting video. Thank you.